Hi, I'm Belle Picone, and today we're going to see if we can fireproof a balloon. The purpose of this lab is to explore thermodynamics. So we already know that heat transfers differently through different mediums. For example, heat is transferred very quickly to liquids and a lot slower in gases. This is because liquids are a lot more conductive than gases are. Today, we're going to use that principle to see if we can create a fireproof balloon. So how do we begin this experiment? First, we're going to want to gather our materials. For today, you're going to need 2 rubber balloons, water to fill one of the balloons, air, your breath will work, and a light source. For us, we're going to be using a lighter. If you don't have a lighter, you can also use a candle or any open flame. However, I don't recommend using your stove because we're going to want to conduct this experiment in a safe, open place that's easy to clean up. Let's jump into our procedure. Take your first balloon and fill it up with air. Once that's done, set it aside and take your next balloon and fill it up with water. To get into conducting our experiment, you're going to want to go into your safe location and light your flame. After that, you're going to want to first take your air balloon and we're going to lower it down onto our flame. See how long that takes to pop. Once that balloon is done, light that same flame, take your water balloon and lower it down slowly. See how long that one takes to pop. Make sure to write down any observations that you make along the way. As for any experiment, it's very important that we make a hypothesis before we begin. For our experiment today, I hypothesized that the balloon filled with water will take a lot longer to pop than the balloon filled with air, and that our balloon filled with air will pop almost immediately when exposed to the flame. Let's go see if we're right. So here we are outside in our safe location, and we have our air balloon. Let's see how long that it lasts. Immediately. Now let's take our water balloon. Let's see how long she lasts. Still nothing. Might have spoken a little bit too soon there. So our hypothesis was correct, but let's explore why. Water has a very high heat capacity, meaning that it will take longer for the water to heat up and cool down than it would the air. Specific heat capacity is the amount of heat required to change 1 mole of the substance by 1 Kelvin. Specific heat capacity of water is 4.184 joules per kilogram of Kelvin. Water is also much more efficient at conductivity and heat transfer. The water at the bottom of the balloon will heat up and become less dense than the cold water. This means that it will rise to the top of the balloon, while that colder water will fill its place at the bottom, keeping the latex at a much cooler temperature. The water is carried to the top of the balloon by convection current, and this is what accounts for the slower pop time of our water balloon. The heat capacity of air is much lower than water, sitting at 1.005 joules per kilogram of kelvins. Let's also keep in mind that gases are a poor conductivity of heat. So while the air at the bottom of the balloon will warm up and become less dense than the cool air and rise to the top of the balloon similarly to how water does, it does this at a much slower rate, giving the latex at the bottom of the balloon a lot more time to heat up, accounting for our quick pop time that we observed. I hope that you found this experiment today helpful and that you were also able to understand a little bit more about thermodynamics and conductivity of different mediums. Thank you so much for watching.